All right, hello again. We are continuing our discussion about reactions, and in today's video we are going to look specifically at something called limiting reactants or excess reactants, and we're going to be diving in a little bit more deeply in looking at chemical reactions. And let's just go right to the Model 1, and let's talk a little bit about Model 1 here, and you'll see quickly, if you haven't already, how it relates to our topic today. So in Model 1 we are assembling a race car, and we have a bunch of different parts here in order to create this particular race car. How many of each part are needed to construct one complete race car? Well, you need one body, you need how many cylinders? Looks like three cylinders, you need one engine, and you need 4 tires. So this is the ratio in which these parts must be assembled in order to create the desired race car that we see here. How many of each part would be needed to construct 3 complete race cars? Well, if I have 3, then I just multiply each of these by 3, 3, 9, 3, and 12. Assuming that you have 15 cylinders and an unlimited supply of the remaining parts. If I have 15 cylinders and I know that each car needs 3, how many complete race cars can you make? Well, 15 divided by 3, I could make 5 cars, and I know that I can always get as many bodies, engines, and tires that I need, but I only have 15 cylinders. Each car needs 3, that's 5 cars. How many of each remaining part would be needed to make this number of cars? Show your work. So it's basically saying if I have 15 cylinders and I need to make 5 cars, I need 5 bodies, I need 5 engines, and I need 20 tires if I have the 15 cylinders. 5 bodies, 15 cylinders, 5 engines, and 20 tires would create my 5 cars. Okay, now we have basically a model here where we're going to put together a car. Again, we are reminded of the parts, and here in this container we have a whole collection of different parts. Just a mishmash of parts, and we're going to try to figure out if we can make any cars out of this collection of parts in container A. So number 4 says count the number of each race car part present in the container A of model 2. So let's see here. I've got 3 bodies. I've got cylinders, those tiny ones here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Engines, I've got, there's a longer rectangle, 1, 2, just 2 engines. And tires, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 tires. Okay, so you kind of already are probably figuring out, if you haven't already figured this out, that these aren't exactly in the ratios that we were hoping for. Okay, so we were hoping them to be in a 1 to 3 to 1 to 4 ratio. 1, 3, 1, 4. We were hoping for a 1, 3, 1, 4 ratio. Well, they're not. They're not in a 1, 3, 1, 4 ratio, and that means that we're not going to be able to probably create the car or cars exactly the way we want to. We might have too many parts of something, or not enough of something. Okay? Model 2, let's complete this by drawing the maximum number of cars that can be made from the parts in container A. Show any excess parts remaining also. So here's the deal. I've got my 3 bodies, so I'm just going to draw those really quickly. Pardon my poor artwork here, my poor sketching. I have to have tires, so 1, 2, 3, 4 tires. 1, 2, 3, 4 tires. I've used up 8, so I'm going to have a tire left over. Okay? I have engines. Do I have enough engines? I've got 2 engines here. Engine, engine. And I have cylinders, 10. So I've got 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 cylinders. Those are cylinders, by the way. All right. So what happened here is I didn't plan ahead very well. I was able to make my 2 cars, but I've got these excess parts that I am not able to use because I ran out of something. Well, as soon as you run out of something, guess what? Production stops. I stopped at 2 cars. I wasn't able to go on because I didn't have enough tires, I didn't have enough engines, and I had the body and the cylinders, but as soon as you run out of something, you're done. You can't put this car together and just have 1 tire and 4 cylinders. So as soon as something in your assembly, in your reaction runs out, that means the production stops and you no longer can make anything. Okay? That's true for chemistry as well. As soon as any of our reactants run out, the production stops. Question number 6. I can see that we have 3 car bodies in container A, so we should be able to build 3 complete car races, or complete race cars. Incorrect, because we ran out of not enough tires and what else? Oh, engines, I think. Okay? Suppose you have a very large number, dozens or hundreds of tires and bodies, but you only have 5 engines and 12 cylinders. Well, if I've got 5 engines, how many complete cars? 5 engines would need, remember 3 cylinders per engine, I would need 15 cylinders. But I don't have 15 cylinders, I only got 12. So I can't even use all of those engines. I've got plenty of tires and bodies. Okay? I'm never going to run out of that. But look what happens here. It is the cylinders that I didn't plan ahead on. I didn't really buy enough cylinders. I didn't even buy enough cylinders to use my 5 engines because I would need 15. I only have 12 cylinders. 12 cylinders, 3 per engine. That means those 12 cylinders are going to go on 4 different engines. Okay? Which means I take all the tires and bodies that I have, I can only make 4 cars. Do you see that the number of cylinders is the one that limits the number of cars I can make? That is my limiting part. My limiting part. Everything else is in excess. I got plenty of tires, bodies. I even have enough engines. I got 1 more engine than I need. All of those are in excess, but it is the number of cylinders that is limiting my production. Okay? Fill in the table below with the maximum number of complete race cars that can be built from each container, and indicate which part limits the number of cars that can be built. Divide the work evenly. Yes, space is provided below the table for each group member to show your work if you need to. And let's look at what we have here. They are giving us, by the way, this reaction. Here is kind of like your chemical reaction. 1 body plus 3 cylinders plus 4 tires plus 1 engine produces 1 car. These coefficients are telling us in what ratio they are reacting, or they are assembled. Okay? So we have the different containers, and I look at this and I say, okay, I got 3 bodies. Do I have enough cylinders for 3 bodies? For 3 bodies, I need 3 times as many cylinders. So I got 3 times 3, yes. Okay? Here's what I'm going to just show you this for a second here. Okay? If you've got 3 bodies, you would need 9 cylinders. This is what you need. I'm just going to write need. If I've got 3 bodies, I would need 9 cylinders. Do I have that? Yes. Okay? If I have 3 bodies, I would need 4 times that in tires. I would need 12 tires. Do I have that? No, I don't. And if I have 3 bodies, I would need 3 engines. Do I have that? No, I do not. So which one is going to limit what I can make? Well, these two I put X's by, but which one is actually the one that is limiting it the most? 2 engines can produce 2 cars. I would need 8 tires. Here's what I need. I need 8 tires. Do I have at least 8 tires? Yes, in that case I do. So it is the engines here that limits how much I can make. I can only make 2. 50 bodies, 12, 50, and 5. Let's do this. Let's just look at the ratio. 1 to 3 to 4 to 1. Are these in a 1, 3, 4, 1 ratio? Okay? So how do we determine that? Well, the best way to determine that is to maybe divide everything in order to find out if you've got the ratio that you desire. In other words, you take the smallest number, in this case 5, and let's divide everything by 5. Take that, everything divided by 5, 5 divided by 5 is 1, 50 divided by 5 is 10, 12 divided by 5, that's going to be 2 and 2/5, and 50 divided by 5 is 10. So now look at this. If I have a 10 to 2 and 2/5 to 10 to 1 ratio, let's compare that. One engine needs 4 tires. Do I have? Yes, I got plenty. One engine needs 3 cylinders. Nope, I only got 2 and 2/5. Problem. One engine needs 1 body. Yeah, I got 10. So here's my problem. Cylinders in this container, I don't have enough cylinders. I can only make, let's see here. In this case, those cylinders, 3 per car, 12 divided by 3 is going to be 4. I can only make 4, and it is the cylinders that are going to cause the problem there. Okay? All right, let's look at this one. If you see that all of these are the same value, by the way, you need the most tires per car. So in this case, the tires are going to be the limiting reactant or the limiting part. 16 tires, I need 4 per car. I can only make 4 cars, even though I've got 16 cylinders, 16 engines, 16 bodies. In this case, it is the tires that are going to stop production. Okay? Let's just do a little comparison here. Let's approach it a different way. Bodies 4, I need at least that many engines. I need, for those 4 bodies, I would need 12 cylinders. I don't have that. And I would need 4 times 4 is 16. I have this. So in this case, it is the cylinders again. And I can only make as many cars as I have cylinders. I only have 9, so 3 per car, that's 3, and it is the cylinders. Okay? Alright, I hope you get the idea here. In this case, I'm just going to share with you, let's see, 20, 24, 36. It usually seems to be sometimes with these numbers, they're kind of close together. It might be the cylinders of the tires this time. 36 cylinders, if I divide that by 3, that's 12 cars. Here I divide this by 4, that's going to be 10. So 10 cars, it is the tires that are going to stop production there. Okay? Alright, Zippy Race Car Company, they build thousands of cars. They do not count individual car parts. Instead, they measure the parts in oodles. Whatever an oodle is, okay? Large number of things. Assuming the inventory in their warehouse below, how many race cars could the Zippy Race Car Company build? Show your work. Okay. So, if we got 4, 5, 8, and 8, whatever oodle is, it doesn't matter. Okay, that could be anything. So the ratio has to be the same though. Remember our ratio up here of 1 to 3 to 4 to 1? I'll remind us, 1 to 3 to 4 to 1. Okay? How many can they build? Well, we do the same thing. It doesn't matter if we're talking about oodles or actual numbers or moles. Doesn't matter. So if we got four bodies would allow us to make 4 cars. Yes, we've got at least 4 engines, and oh, we don't have enough tires though. Nor do we have enough cylinders, I think. So we have to look a little bit deeper. No problem with the engines. Cars, it looks like we might have a problem there with tires. Oh, sorry. Tires, we only have 8. We need 4, so this would only allow us to make 2. Do I have enough cylinders for 2? Nope, because I need 3 per engine. So this is really going to hinder us. So I can only make 1 oodle of cars because I've got 3 oodles there and only 2 left over in order to make the other cars. Okay, I can make 1 oodle. Actually, I can make, I suppose if you think of it this way, I can make 5 divided by 3. So 1 2/3 oodles of cars. Okay. All right. If we consider these ratios, I hope you noticed that we're kind of using ratios here like we used mole ratios before. If I have a particular number and I want to find out how much of something else I need, I can use my ratio to figure out how much of that other part I would need in order to make a complete number of cars. It's not necessary to know the number of parts in an oodle to solve the problem because, again, we are working with ratios. Ratios, it doesn't matter if it is 1 or 100 or a mole or an oodle. It is the ratio here that is going to determine how much gets produced. Is the component with the smallest number of parts always the one that limits production? No. You can't just look up here and say, oh, you know what? 4 is the smallest number, therefore it must be the bodies that are going to run out first. No, that's not the case because you only need 1 body, whereas you need 3 cylinders per car. So you have to look at the ratio here and figure out which one is going to get exhausted first, which one's going to get consumed first by looking at the ratio and the number that you have. All right, now we're looking at chemistry. It's going to come back to chemistry. We're going to apply this now to the concepts that we've been talking about with mole ratios and limiting or excess reactants. Each of this diagram, each of those represent a mole, not just a particular molecule, but that's 1 mole of hydrogen molecules. Okay, each of these diagrams represents a mole of oxygen. Okay. So each of those represents 6.022 times 10 to the 23rd particles of that particular molecule. Here's our reaction. 2 moles of hydrogen react with 1 mole of oxygen to produce 2 moles of water. All right. Here is our container. These particles start bouncing around in there and banging into each other and reacting to produce our water. And let's see what happens. Refer to the chemical reaction in Model 3. How many moles of water molecules are produced if 1 mole of oxygen completely reacts? Just 1 mole. 1 mole of oxygen is going to react with 2 moles of hydrogen to produce 2 moles of water. How many moles of water are produced if 1 mole of oxygen molecules completely reacts? I assume they're making the point that you've got plenty of hydrogen. So you're going to create 2 moles of water. Okay? How many moles of hydrogen molecules are needed to react with 1 mole of oxygen? So if you have 1 mole of oxygen, you need 2 moles of hydrogen. Okay? Model 3, let's see, we need to draw the maximum number of water molecules that can be produced from the reactants shown and draw any remaining moles of reactants in the container after the reaction as well. So basically, these are going to react in a 2-to-1 ratio. Here's how I'm going to do it. I'm just going to kind of group them together. So we've got these two combining with an oxygen. I've got, let's say, these two combining with that oxygen, and then these two combining with that oxygen, and this poor guy here is all by himself. All right, so we're going to have how many? Every 2 to 1 produces 2. Every 2 hydrogens and 1 oxygen produces 2 waters. So I'm going to have water. I'm going to have another water. I'm going to have how many waters here? For every one of these circled groups, I'm going to be producing 2 waters. That's 2, 4, 6. All right, and then a pair of hydrogens left over. There's your hydrogen molecule left over that did not find anything to react with. So we're going to ask this question. I know it's going to be asked. Which one of these is the limiting reactant? It is the oxygen. The oxygen's all gone, and we have some hydrogen left over. Okay? Which reactant limited? It is the oxygen. Which reactant, hydrogen, was present in excess and remained after the production was complete? There you go. Fill in the table below with the maximum moles of water that can be produced in each container. Indicate which reactant limits the quantity of water produced. This is the limiting reactant, and we're going to find out which one is in excess and how much will be left over. And we have here determine the maximum number of moles of water produced and the moles of reactant in excess. Okay, so if we look at this, we got 7. Let's remind ourselves of the ratio here. 2 to 1 to 2. 2, 1 to 2. Okay? If I've got 7 moles of hydrogen, 7 moles of hydrogen would produce, if I use all 7 of those, it would produce it would use up half as much oxygen. I would need half of 7 is 3.5. Do I have 3.5? Nope, I only got 3. So therefore, this is my limiting reactant, and I only have 3. So 3 is going to be used up. When it's used up, I'm not going to use all 7. I'm actually only going to use double that. I'm only going to use 6. I'm not going to use 7. 1 is going to remain, and this 3 right here is what is going to determine how much is produced. Water is produced in a 2 to 1 ratio when looking at oxygen, so that's why 6 are produced. Oxygen is the limiting one. I have 1 mole of hydrogen left over. So let's do this again. I have 8 of hydrogen. If I use up all 8 of hydrogen, I would need half as much oxygen. I would need 4. Do I have 4? No, I don't have 4. So in this case, I only have 3. So again, I'm going to produce 6 waters, and I'm going to have only 6 of this. 6 of the hydrogen is going to react with it. I'm going to have 2 remaining of the hydrogen. Okay? Oxygen again, 2 moles of the hydrogen left over. Alright, let's continue. If I have 10 of hydrogen, I would need half of that in oxygen to consume all the hydrogen. So I would need 5. Wow, perfect. Okay? I have exactly what I need. So both of these are going to be exhausted completely, consumed completely, and I'm going to produce twice as much water as the oxygen, so 10, same number of moles as the hydrogen, and limiting reactant, you could say that either both or none. Okay, I guess they both limited it, or you could say since neither of them really is gone first, you could say none, there's neither, and you don't have any, nothing. Okay? They have a perfect ratio. They're in a 2 to 1 ratio, 2, 1, 2. Okay? If I've got 5 hydrogen, I would need half of that. I would need 2.5. Do I have that? I've got plenty of oxygen. So I got to look the other direction. Okay? You got plenty of oxygen. That's all going to get used up. Sorry, the hydrogen's all going to get used up. And I always produce the same amount of water as hydrogen. But I'm not going to use all of this oxygen. I'm going to have 2.5 in excess. 2.5 in excess. Your limiting reactant is the hydrogen. You're going to have 2.5 of oxygen left over. 8 of hydrogen, I need half as much oxygen. I need 4. Do I have 4? Yes, I got 6. More than I need, so therefore I'm going to have 2 moles in excess. Hydrogen is the limiting one, and you always produce the same amount of water as a hydrogen used up. And that would mean 8 of this as well. You could use this 4 if you wanted to, but don't use the 6. You don't use 6 moles of oxygen. You only use 4. You could use 4 and double it because it's a 2-to-1 ratio, but don't use the number that is not all consumed. Never use that number to find out how much is produced. Okay? Is the reactant with the smaller number of moles always the limiting reactant? We already talked about this. It is not. You have to look at the ratio. You must look at ratios and quantity. Okay? You can't just look at the smallest number. All right, let's see how some people approach this. These are different calculations that could be performed to find the limiting reactant. And let's see what they did here. They took 8 moles of hydrogen. They're taking the molar ratio. This is for between water and hydrogen. And they say 8 moles of water produced. They take 6 moles of oxygen, and they're taking the molar ratio between water and oxygen. And they're saying 12 moles of water. And they're saying, well, you can't produce 12 moles of water with 6 moles of oxygen if you only can produce 8 moles of water with 8 moles of hydrogen, assuming that you've got these two quantities as reactants. So basically what they're saying is calculate the amount produced from each of the reactants individually, assuming the other one is in excess, and then compare. Well, you're never going to get the larger amount if the smaller amount is as a result of the limiting reactant. Okay? As soon as you create 8 moles of water right here, this 8 moles of hydrogen is going to be gone. You will have used up 4 moles of the oxygen, and you're going to have 2 left over. So you'll never get to the 12. So this is one way to figure out who's the limiting reactant. It's whichever one produces the lesser amount of product. Let's look at this one. 8 moles of hydrogen, and now we're looking at the oxygen to hydrogen ratio. That is a 1-to-2 ratio, so 8 moles of hydrogen would react perfectly, in a perfect ratio, with 4 moles of oxygen. That's what you need. And you've got more than you need, so that means that the hydrogen is the limiting reactant. And then to figure out how much would be produced, you use that 8 moles. Don't use the 6 moles of oxygen. Use the 8 moles to find out how much water is produced. Okay? So either way is fine. And whichever one you find to be easier or most logical for you, you can use that method. Okay? Or if you came up with a different way of thinking of it, that is fine as well. Okay? All right. I hope this is helpful. Let's look at the extension questions and talk a little bit about the reaction continuing here with hydrogen and oxygen. It says, consider the synthesis of water. As we talked about before, a container is filled with 10 grams of hydrogen, 5 grams of oxygen. So let's write down hydrogen and oxygen producing water. If we balance this, we have to have a 2 and a 2 there. 2, 1, 2. Which reactant, hydrogen or oxygen, is the limiting reactant in this case? Show your work. All right, notice that we are given masses here. We're not given moles. Be very, very, very careful here. This is 10 grams. This is 5 grams. I'm going to encourage you to think back to a previous video when I kind of set up a table here with moles, molar mass, and mass, because in order to find the limiting reactant, you have to look at mole ratios, not mass. So we are given hydrogen, 10 grams. We are given oxygen, 5 grams. And I'm going to find out how many moles each of those are. And the molar mass of hydrogen, H2, is 2 grams per mole. The molar mass of oxygen, O2, is 32 grams per mole. All right. So if I find out how many moles that is, 10 grams at 2 grams per mole, if I divide by 2, 10 divided by 2, that's going to give me 5 moles here. And if I take 5 divided by 32, 5 divided by 32 is about 30, so it's about 1/6, okay? So you can see here I've got very little oxygen compared to the moles of hydrogen. Even though it doesn't look like those masses are that much of a difference, oxygen is so much heavier that 5 grams of oxygen is a small fractional amount of moles here. Okay? So if I have 5 moles of hydrogen, I need 2.5 moles of oxygen. I don't even have that. I got less than 1/6 of a mole. Okay? So that means that my 1/6 of a mole, or my 5/32 of a mole, okay, this is grams and grams per mole. This is going to then give me how many moles of oxygen I have. If I want to find out how much water is going to be produced, I can't use my 5 moles of hydrogen here. I can't use, not all 10 grams of the hydrogen are going to be used up. All 5 grams of the oxygen, yes, because that's my limiting reactant. So to fully consume all of the hydrogen, I need 2.5 moles of oxygen. I don't have 2.5. So this is my limiting reactant. So I take that amount, the number of moles of oxygen, and I use my ratio of 2 to 1, 2 moles of water for every 1 mole of oxygen, and that tells me how many moles I'm going to get. So remember this here, when I do this calculation, 5/32, this is actually going to be moles. Grams are going to cancel. So 5/32 times 2, that's going to give me 5/16 of a mole. And if I want to find out how much water that is, 5/16 of a mole of water, and then I multiply by the molar mass of water, which is 18 grams per mole. So 5 times 18 divided by 16, so that value is going to tell you how many grams of water you can produce. Okay? And I just did that right there. Which reactant is present in excess? That would be your H2. What mass of the reactant remains after the reaction is complete? Oh, that's a great question. So if you look here, we used 5/32 of a mole of oxygen, and I would use twice that of hydrogen. So if you use 5/32 moles of oxygen, and I would use twice that for hydrogen. Every 2 moles of hydrogen react with 1 mole of oxygen. So I'm going to have 5/16, same as the amount of water, by the way, moles of hydrogen, and then what mass of that reactant remains. This is how much is going to be used. So then I would multiply this by 2. Okay? Let's take this 5/16 times 2, because it's 2 grams per mole, and this is the number of moles here. So this is going to be 5/8 grams of hydrogen used. So how much is not used? Well, you're just going to take your 10 grams here minus the 5/8, and that's how much is in excess. Okay? All right, I hope this is very helpful for you. This is a very important concept because the amount that is produced is dependent on that limiting reactant. So many times when there's manufacturing or there's a production of some type, you want to know, what do you need enough of? Or am I going to run out of something? Because that's going to stop production, and it's very important to not run out of something if you want to have a maximum yield. Okay? So we're going to continue to talk a little bit about reactions in the future, and do some more stoichiometry, and continue to talk about limiting and excess reactants. Everything actually that we are learning, we're going to be dragging with us as we move forward in this course. All right, great job, and we'll see you in the next video.